vertical axis wind turbines could revolutionize offshore wind power. Wind energy is not a new thing. Wind pushed boats up the Nile as early as 7,000 years ago, and simple windmills were pumping water in China 2,000 years ago. Fast forward to today, and the same fundamental principles are assisting in the rapid and efficient creation of renewable and sustainable energy. Offshore wind farms are being built because there are no physical constraints in the oceans, such as hills or buildings, which could obstruct wind flow. But the 260 meters tall wind turbines are still not making most of the offshore wind energy. How are engineers planning to harness the majority of this energy? And how efficient are the new innovative vertical axis turbines? Let's jump into the video to find out. The tremendous economic potential of cutting-edge technological advancements is what makes renewable energy so fascinating. A recent discovery by Oxford Brookes University School of Engineering, Computing and Mathematics engineers could forever change the design of offshore wind farms. The study, led by Professor Iakovos Tsanakis, shows that replacing the traditional horizontal axis wind turbines with vertical axis wind turbines can result in a 15% increase in power output for deep sea and coastal wind turbines. While horizontal axis windmills use a standard 3-blade pinwheel design to generate energy, vertical axis windmills use a more cylindrical shape with blades rotating around a central shaft. For several reasons, vertical axis wind turbines are a promising technology for floating offshore wind. Firstly, they could accept and use wind from all directions, so they don't need heavy, expensive technology to point them into the strong wind like horizontal axis wind turbines do. Second, they can operate their generators at or near the water's edge. Horizontal axis wind turbines must mount this heavy gear directly on top of their support towers where the main axle is, resulting in a top-heavy design that necessitates extreme power strength and massive counterweights beneath the surface to keep them upright. More strength means more materials, which means more money. Third, because they produce little wake downwind, they can be deployed much closer together than horizontal axis wind turbines. Horizontal axis wind turbines must be spaced farther apart, lowering their yield for a given project area. SeaTwirl, a Swedish company, is developing and testing vertical axis offshore wind turbines. They claim that their floating vertical axis wind turbines can significantly reduce the cost of deep offshore wind energy. 3 vertical axis blades are rigidly mounted on a long, buoyant pole with a low center of gravity and a heavy weight at the bottom acting as a center of gravity. This is contained within a static generator ring that is anchored to the sea floor. The entire pole spins as the wind catches the blades, and the generator yields energy and transmits it back to the shore via cables. The generator's bearings do not have to bear the weight of the entire structure because the main tower is buoyant and held more or less upright by the deck. As a result, they can be smaller, lighter, and less expensive. Maintenance, as with other vertical axis designs, should be much easier and less expensive than with horizontal axis wind turbines, because the parts that need work are located near sea level rather than on tops of enormous towers. As a result, these can be maintained without the use of exorbitantly expensive crane ships. The main problem with conventional horizontal wind farms, which can have 60 to 70 turbines spread across 1,500 acres, is that efficiency degrades rapidly in the back rows due to turbulence from the formation's first rows. Vertical axis turbines address this problem by producing less turbulence and, in some cases, improving the efficiency of nearby turbines. Additionally, the effects of the downstream generated turbulence reduce traditional designs' back row efficiency by 25 to 30%. The average offshore turbine is massive, measuring 220 meters across and 248 meters tall, and producing 12 to 14 megawatts of power. Wind turbine capacity in the United States currently stands at 118 gigawatts, accounting for 8.4% of utility-scale energy production. Offshore wind capacity is 42 megawatts, led by the first offshore wind farm at Block Island, Rhode Island, which accounts for 30 megawatts. In addition to the recently announced Vineyard Wind project, which will provide 800 megawatts, the Danish company Ørsted is working on 2 ocean wind projects that will provide a total of 2.3 gigawatts to the state of New Jersey. Wind turbine technology was first used in remote small-scale applications such as research stations that were disconnected from the power grid in the 1970s. The most significant hindrance to the advancement of vertical axis designs is the lack of a proper airfoil shape and issues with braking systems, which drive unit costs up. Traditional aerospace applications provided years of research and technical foundation for the development of the commonly seen pinwheel design. The offshore wind turbine market is driven by a 3-rotor horizontal axis design that is the industry standard, but there is no standard design for vertical axis wind turbines. Recent investments in offshore wind farms, such as the Vineyard Wind project, employ a standard 3-rotor horizontal axis design provided by market leader GE Renewable Energy in a bedrock-based application unsuitable for deep water. Given the harsh and unpredictable conditions of deep ocean water, not to bring up the weight and balance of a wind turbine, it's understandable that the technology required to mount a floating turbine was developed relatively recently. Sandia National Laboratory developed a proposed solution in collaboration with the Department of Energy and universities across the United States. Much of Sandia Labs' work involved simulating offshore wind projects. Improvements have also been made in the design of airfoils and mechanical generators, as well as in the methods for securing a turbine for safe operation in deep water conditions. Vertical axis market solutions are currently focused on microgrid and extreme weather applications. They have the inherent advantage of being able to perform well in stressful weather environments, and turbines can operate even during hurricanes, which can be a lifesaver for deep ocean water infrastructure such as oil wells. Nations such as the United Kingdom and Germany are already at the forefront of offshore wind production capacity and investment. The first GE-made 12-megawatt offshore unit, the same design used in the Vineyard Wind project, is installed in the British Isles. British interests are concentrated in coastal sea applications, where the horizontal axis design offered by GE allows for easy management of conditions. The Block Island wind farm, located 3 miles off the coast of Rhode Island, produces 30 megawatts from a series of GE units, enough to power 27,000 homes. Deep sea wind energy is currently used by few countries because it can cost twice as much as the coastal alternatives in terms of levelized cost of energy. Offshore wind has found a niche application for offshore power generation. The oil industry, which currently powers platforms with diesel-electric generators, is one of the most demanding clients for offshore energy. The average offshore oil well uses 5,200 to 8,000 gallons per day. This application enables a high levelized cost of energy, such as offshore wind, to be considered competitive. Equinor, a Norwegian multinational energy company, focuses on using offshore wind to power their oil platforms. The proposed high-wind Tampen project includes 11 floating horizontal axis turbines with a total capacity of 88 megawatts, which could meet up to 35% of the energy demand for a series of 5 offshore platforms. The high-wind project is expected to reduce CO2 emissions by 200,000 tons per year. Additional investment in offshore wind technology may eliminate the need for diesel fuel entirely. There have been small-scale projects in the United States to test the designs of floating wind turbines. The Deep Wind Consortium, in collaboration with the University of Maine, installed a scale model off the coast of Maine in 2013. Principal Power, based in Seattle, has installed their patented wind float design in a deep-sea application off the west coast of the United States. Principal Power currently has 5 units in operation and has demonstrated the ability of their design to withstand up to 17-meter waves and 92 miles per hour wind. If the United States continues to invest in the development of floating vertical axis turbine technology, it has the potential to become the global leader in deep-sea wind. When the proper technology is used, the production capacity of a deep-sea wind farm is infinitely scalable once it overcomes the technical barriers created by materials and mechanical systems. That pretty much wraps up this video, guys. What are your thoughts on vertical axis technology? And how effective do you believe it will be in reducing carbon emissions? Let us know in the comments below. Thanks for watching. Remember, make sure to subscribe to this channel with bell notifications on if you enjoy watching our content. We upload some pretty awesome stuff here, which you will most certainly enjoy. So hit a like on this video, leave a comment below, and see you guys in the next one.